Deep learning has completely turbocharged modern AI. This incredible algorithm that can automatically detect the important features, out of data. And from this algorithm, it could construct hierarchically knowledge representations. And these knowledge representations, if you give it enough information, if enough data, it would become more and more robust and recognize a larger diversity of that space, become more intelligent. Deep learning has revolutionized modern AI. The thing that deep learning needs, though, is a ton of data, and more importantly, a ton of compute. And the reason for that is it just iteratively goes through and tries to figure out what are the important features using all of these incredibly revolutionary algorithms. Our strategy at NVIDIA is to advance GPU computing for deep learning, for AI, at the speed of light. From the processor development to the systems, the interconnects, the way we construct systems, to all of the software layers that are on top of it, making it available and partnering with cloud service providers and OEMs everywhere. Irrespective of what AI framework you use or what AI network you're trying to create, wherever you are, we will support it. And we will support it from end to end, so that the frameworks that you use to develop the networks and models will be deployable in large scale. And we would even make it possible for you to access our platform in every possible way and in any sort of way. Whether you would like to build a personal supercomputer for a few $1,000s with our Titan V, or to be able to rent time in the cloud for a few dollars an hour, or to be able to build your own supercomputing cluster, or just to buy one from us. We're going to make it possible for you to do your work at the speed of light and to be able to do it anywhere. Today, we're announcing several big things. First, we are doubling our GPU. The Volta V100 is now 32 gigabytes of HBM2 memory. It's twice the size of what it used to be. Now, this is so important, and the reason for that, and I'll show you later, the networks are getting larger and larger and larger. And so it doesn't fit in 16 gigabytes. Researchers would like to not worry about memory size while they're developing their neural networks, and 32 gigabytes gives them just a lot more space. HBM2, the fastest memory in the world, connected to the Volta V100. It'll be available as of now, and the next DGX as you buy, it'll be available in the cloud very, very shortly. It is in complete volume production everywhere. The new Volta with 32 gig. Neural networks are growing and evolving at an extraordinary rate, at a lightning rate. What started out just 5 years ago with the AlexNet, Alex Krizhevsky's now world-famous AlexNet, was 8 layers deep, had millions of parameters. 8 layers deep, millions of parameters. 8 layers deep and millions of parameters. It's a CNN. The CNN was first developed and produced or created by Yann LeCun, and the training technique is called stochastic gradient descent by Jeff Hinton. And it was implemented in AlexNet for the very first time, and it won the ImageNet competition. Well, 5 short years later, thousands of species have emerged. Thousands of species of artificial intelligence networks, models of all different types, from the CNNs of Yann LeCun to the RNNs that was first done at Schmidhuber's lab in Switzerland, the generative adversarial networks of Ian Goodfellow, the deep reinforcement learning that was most recently done by DeepMind, Demis's DeepMind, and Peter Beal over at Berkeley. All of these different architectures have hundreds of different implementations. The number of species is growing so incredibly, and there are so many new ones coming out. Hinton just recently disclosed the capsule net so that it could not only recognize images in its image form, but to learn the geometric form of the images. So many new techniques. Neural collaborative filtering, NCF, which is used for recommenders. What started out just 5 years ago as 8 layers and a few million parameters is now hundreds of layers and billions of parameters. 8 layers and millions of parameters to hundreds of layers, billions of parameters. Neural network models have increased in complexity, not to mention the number of species, the thousands of species that are now out there. Neural network models have now grown in complexity 500 times. In just 5 years, 500 times in 5 years. Remember, Moore's law would have only kept up with 10x of that. 500 times in 5 years. So the world wants, the researchers all over the world wants just a gigantic GPU. Not a big one, a gigantic one. Not a huge one, a gigantic one. And so, ladies and gentlemen, today, I would like to announce the world's largest GPUs. This is the world's largest GPU. This is 16 Volta equivalents connected by 12 brand new high throughput switches that the world has never seen. It's called MV switch. These 16 Tesla V100 equivalents, each with 32 gigabytes, creates virtually a 512 gigabyte memory. Not only that, these 512 gigabyte memories, the way you address the memory and the way that every single GPU could talk to the memory of another GPU, completely using the same memory model. The memory fabric semantic on our chip that connects all of the processors have been extended out of this chip, out of the GPU, onto the MV switches, connecting each and every one of them. In total, 14 terabytes per second of aggregate bandwidth. 14 terabytes. So that's, what is that? Let's think about that. 14,000 gigabytes. And let's say if a high-resolution movie is 10 gigabytes. Okay? So 14,000 gigabytes, 1,440 movies. 1,440 movies. More movies than any human has ever seen could be transferred across this switch in 1 second, like that. Ladies and gentlemen, 14,000 movies. $14,000 movies downloaded in 1 second. Dream come true. Altogether, 81,900 CUDA cores, 2 petaflops. This GPU is 2 petaflops. I told you earlier, the fastest supercomputer on the planet is 125. The fastest supercomputer in America is 100 petaflops. This is 2 petaflops of tensor cores for AI on this GPU, the world's largest GPU. Let me show it to you. No, that thing. Hang on a second. You know, guys, here's the thing. We're so busy pulling this stuff together, we don't rehearse. Okay, our rehearsal is basically grip it and rip it. Ladies and gentlemen, the world's largest GPU. You didn't fall for that, did you? You didn't fall for that. Hang on a second. This isn't the world's largest GPU. This is the world's largest GPU. Guys, it's sitting in plain sight, hiding in plain sight right here. Sandy, if I could give that to you. Now, I understood earlier that was that the game plan for me to do this myself? Oh, okay, it wasn't? All right. Ladies and gentlemen, grip it and rip it. This, ladies and gentlemen, is the world's largest GPU. Now, what you're looking at is something that's really, truly amazing. So let me show it to you this way, and I'll come back to that. Okay? This switch has 2 billion transistors made of TSMC's 12-nanometer FinFET. This great process. Every one of these switches, and there are 12 of them, every one of these switches has 18 links, which are 8 bits wide, 18 MV links, 8 bits wide, with a SerDes that's moving at 25 gigabits per second. 25 gigabits per second on just one signal. There's 8 of them per link. There's 18 links on this one chip, and it's bidirectional. Altogether, it creates 7.2 terabits per second, or 900 gigabytes per second. So 900 gigabytes per second, by the way, of bandwidth, well, that's a lot of movies too. So 7.2 terabits per second, 900 gigabytes per second, goes through one switch. There are 12 switches. 12 switches. What that basically says is that every single GPU can communicate to every other single GPU at 20 times the bandwidth of PCI Express. Isn't that amazing? Every single GPU can talk to every other GPU. And every single GPU can talk to every single GPU in a non-blocking way. It's a fabric. It's not a network, it's a switch. It's a non-blocking fabric switch with a memory semantics, memory programming model that's exactly the same as what's inside our chip. And therefore, all the reads and all the writes and all the atomics just works across this. The bandwidth and the performance and the latency of this switch is incredibly low. It's incredibly low. Unlike a network, this is a switch, which means every single GPU can talk to the other GPUs with extremely low latency. You want to read, you want to synchronize a parameter, it takes no time. 300 gigabytes per second. And altogether, NVIDIA's largest graphics card, this is what it looks like. The largest graphics card, the world has ever made. The largest graphics card the world's ever, 2 petaflops, 512 gigabytes. Most graphics cards in the world today, 2 or 3 gigabytes. 2 or 3 gigabytes. This is 512 gigabytes. 10,000 watts. 10,000 watts only. Only 10,000 watts. Only 10,000 watts. The amount of airflow is really quite amazing to cool it. And we designed this porous fabric in air intake in the front. It looks beautiful, but it's incredibly functional. Air comes traveling through it, flows through all of our chips. 10,000 watts of energy, power is being thermal managed. 350 pounds. No human could lift it. No, 350 pounds. The first time I saw that, I was thinking, I could lift that. Didn't move. And I'm fairly strong, upper body strength. And so 350 pounds. What's inside it is 16 Tesla V132 gigs with 12 MV switches. And it's got this incredible what's called a plane card. It basically has 200 times. It has 200 times the bandwidth of the highest speed NIC on the planet. So imagine it's like 200 NICs of connecting the top to the bottom, connecting the top GPU tray to the bottom GPU tray. Each NIC, call it $1,000, $2,000. Call it $1,000. $200,000 of NICs would be required to connect the top to the bottom. It has that much bandwidth. It has that much bandwidth. If we were to use networking cards, well, we still have to connect multiple of these, and so we have 8 of the world's highest speed NICs from Mellanox to connect multiple of these systems together. It has the two fastest CPUs we can possibly buy, the Xeon Platinums. 30 terabytes of storage. 30 terabytes of storage on the system, because as you know, we're going to crunch through a lot of data really, really fast. So all together, ladies and gentlemen, it looks like this. This is the NVIDIA DGX2, the world's largest GPU, the world's largest add-in card, 2 petaflops, 512 gigabytes, 350 pounds, and just beautiful. This is what an engineer finds beautiful, you guys. This is sexy. This is beautiful. This is unbelievable, incredibly beautiful. And guys, did you guys notice the animation? NVIDIA's artists are so spectacular. This entire animation was shot with 112 shots. It's photographed, it's stop motion animation. This is not 3D. You know that we could do it in 3D, but we chose not to. Why? Because it's more fun. You guys want to see it again? Oh, stop motion animation, guys. Check it out. Guys, I love you guys. It's incredible. Tim Burton, you got nothing on us. Look at that. The world's largest GPU, 350 pounds. Well, let's see what it can do. 10 times faster than DGX1. Does that even make any sense? 10 times faster than DGX1. And so this is 6 months ago. This is literally 6 months ago. We showed these numbers. And the entire stack, look at the entire stack. There's so much software that's necessary to build this. This is a high-performance computer. It's a supercomputer designed for deep learning. And so look at this entire stack of software that was optimized. As a result, running PyTorch, the framework, and training FairSeek, the sequence-to-sequence model used for natural language, used for machine translation, literally took 15 days on a DGX1, which was a world record at the time, and now it takes 1.5 days. Well, the amazing thing is, the researchers don't have 13 days left to sit around. The researchers are now using all kinds of techniques to use AI to create AIs. And so the number of experiments, the number of permutations, the exploration space of AI, sweeping through all the different configurations of architectures and the way to compose it, the number of layers, the training rates, sweeping through all of those hyperparameters and sweeping through all the different architectures at the same time is going to create just hundreds of experiments at one time. And so as a result, with bigger networks, more data, more experimentation, DGX2 couldn't have come at a better time. And so it is 10 times in 6 months. Now, the thing that's really amazing is this. How much should we charge? I mean, look, it took hundreds of millions of dollars of engineering. It took hundreds of millions of dollars of engineering. This is the first unit, so this is, call it $250 million. And for just an incredible friend-to-friend price of $1.5 million, it seems like it doesn't even seem fair. It doesn't seem fair at all. Nah. Ladies and gentlemen, $399,000. You guys understand there are only 2 themes in this conference. That's right. The more you buy, the more you save. Okay? This front row's got it. We're going to keep working. All right? The more you buy, the more you save. And so $399,000 for the world's most advanced, most powerful computer. This is what it replaces. 300 dual CPU servers, easily for $3 million. Easily for $3 million. Easily for $3 million. But the important thing is 180,000 watts, 180 watts, in order to train FairSeek in 1.5 days. Well, it only takes one of these beautiful DGX2, just one DGX2, 10,000 watts, only 10,000 watts. 1/18 the power, 1/8 the cost. The more you buy, the more you save. It's incredible. You know, it's truly amazing how far we've come in just the last 5 years. We started talking about deep learning about 6 or 7 years ago, and at the time, the effectiveness wasn't anywhere near what it is today. 5 years later, since AlexNet, the progress that we've made is literally incredible. And I think it'd just be kind of fun just to do a report card, see what happened in the last 5 years. This is what it looks like. This is what Alex Krizhevsky trained AlexNet on. Two GTX 580s. Two GTX 580s. And it took him 6 days. But those were 6 worthwhile days because he became world famous, he won ImageNet, and kicked off the deep learning revolution. 5 years later, we could train it in 18 minutes. 5 years later, we could train it in 18 minutes. 500 times faster. 500 times faster. Isn't that amazing, guys? To be able to do a task 500 times faster in 5 years. To be able to do any task 500 times faster. Any task of great importance 500 times faster. Or to be able to do a task of great importance 500 times larger in the same time. This is some kind of a supercharged law that we're experiencing. Well, one of the things that made it possible, of course, is what I said earlier. This is an innovation that is not just about a chip. This is an innovation about the entire stack. Everything was touched. Thousands of engineers all over our company, from VLSI to process engineering to package engineering to circuit design, to architecture to chip design, system software, solvers and libraries and algorithms and systems, all got involved. This is the effort, this is the work, this is the body of work of literally every single employee at NVIDIA. We are all in on deep learning, and this is the result. And so over the next several years, it's going to be just utterly incredible because we're just picking up steam. This is some new type of computing. The amount of data is growing exponentially. There's evidence that with GPU computing, the computation is growing exponentially. And as a result, deep learning networks and deep learning models, AI models, are growing in capability and effectiveness at a double exponential. At a double exponential. More data, more computing, both on an exponential growth, compounding together into some kind of a double exponential for AI. That's one of the reasons why it's moving so fast. Really, really exciting times. The system is complicated, and the software is complicated. And so what we've done is we've created containers to containerize all of these complicated softwares that are optimized into one container at a time. We put them into Tupperwares, if you will. And by putting them into these Tupperwares, we put them up in the cloud. We call it the NGC, the NVIDIA GPU Cloud. The NVIDIA GPU Cloud is not cloud computing. NVIDIA GPU Cloud is a cloud registry of all of these containers. 20,000 organizations have downloaded our containers. It's running in clouds, it's running in data centers, it's running all over the place. These NGC containers are just completely fabulous. And the reason for that is because irrespective of what cloud you run on, it's exactly the same stack. Because all the clouds have NVIDIA GPUs. All of the clouds now can run these stacks. All you have to do is come to that registry. You log in, you download, you run. You log in, you download, you run. It's about like that. 1, 2, 3, easy peasy. 20,000 registered users or organizations, a lot more users, 30 containers. Last year when I stood here, there were a handful. We've updated them, improved them, enhanced them, and we added a whole bunch more to them. And NGC has now been certified. We've certified. We have to test each and every one of these architectures on the data centers that we run on. We've certified AWS, and just today, we're announcing that Google Cloud Platform, GCP, Ali Cloud, Oracle Cloud will also be certified, has also been certified. Okay, so now they're available on multiple clouds. This is the only architecture that is any cloud. And in fact, it also runs obviously on DGXs, so it runs on any cloud and in-prem, so that's hybrid cloud. So ladies and gentlemen, our latest release of NGC. Plaster. Programmability, because the number of network species is growing exponentially. And they're evolving, they're getting more and more complicated. Latency, because without low latency, you can't have a good quality of service. Accuracy. If your model isn't accurate, there is no way that it could predict the right answer, or more importantly, revenues get hurt. Quality of service is compromised. Prediction is compromised. Size. The smaller these networks are, the more of these services we can fit in a data center. Throughput. Ultimately, these data centers are enormous capital investments, and the higher the throughput for the billions of people who are using it, the lower the cost, the more money you save. Energy efficiency. We are consuming a lot of energy all around the world. We need a computing model that dramatically reduces energy. Energy efficiency and rate of learning. Rate of learning. In machine learning, it's about the amount of data you have, the amount of computing you have, but ultimately it's about how fast you're learning. The more new data you have, the faster computers you have, the faster rate of learning. You're going to deploy the model. You're going to learn from the new experiences. You're going to collect new data. You're going to train the current model. You're going to deploy it. That rate of learning is what defines success in the new world of machine learning. Ladies and gentlemen, I invented this word. Plaster. The second thing I want you to remember today, this is not a complicated conference. More you buy, the more you save. And number two, inference is complicated. Anybody who thinks that inference is easy, you know what, I'm just going to go buy a ASIC, stick it in my data center. Here's an ASIC, here's an FPGA, I'm going to stick that in my data center. Unfortunately, we know that hyperscale data centers are the most complicated computers the world has ever made. It's the size of these rooms. Billions of dollars are dedicated to it. It serves billions of people. How could it be simple? Building one computer for one user is plenty hard enough as it is. Building a supercomputer, hyperscale, that serves billions of people, delivering great quality of service while minimizing operational cost, it can't possibly be easy. Inference is hard because everything matters. Programmability matters, latency matters, accuracy matters, size matters, throughput matters, energy efficiency matters, and rate of learning matters. God, how did I do that? Come on, you guys, that's fairly good. I was trying to figure out how I was going to explain the complexity of inference last night. This is it. Brand new slide. Just one slide. We're done. plaster. So we've dedicated just an enormous amount of resources to solving this problem for inference, for hyperscale data centers. Their workload is really complicated. From image and video workload, natural language understanding workload, recommendation systems, recommenders, speech synthesis, speech recognition. They have all kinds of different types of networks. Sequence-to-sequence networks, deep generator networks, something perceptron. What's MLP? Where's Mike Houston? Multi-layer perceptrons, for God's sakes. Neural collaboration filters. Okay, recurrent neural networks, CNNs, of course. And so we started working on TensorRT, which takes the output of these frameworks, which are these massively complex computational graphs, and we have to target for all of the parameters that I just told you about. And we got to make that network as small as possible, as high performance as possible, and yet retain all of its accuracy. And each one of the target devices, of course, are a little different because our GPUs for deployment are different than the GPUs for training. And so initially, 1 year ago, we announced CNN. And then 6 months later, we announced 8-bit integer so that we could have multiple types of precision so that we could adapt for which one of the networks could lose a little precision at the benefit of a lot more throughput. We then supported Tensor Core 6 months ago. Today, we're announcing the largest battery of new tools, the largest battery of new algorithms and new libraries for inference that we've ever announced. First of all, TensorRT 4.0. Brand new TensorRT. It now has the ability to handle recurrent neural networks, sequence to sequence. It has deep integration into TensorFlow. I want to thank the engineers at Google who took TensorRT and our compilers and integrated it natively into TensorFlow. And so in the future, when you're done training the network, you could run that network fully optimized right on the target device. We worked with the team of Kaldi framework, the most popular voice recognition, speech recognition framework called Kaldi, has now been fully optimized for TensorRT, for NVIDIA's architecture. And then lastly, Onyx, a brand new backend that supports PyTorch, supports MXNet, supports Windows, and has the same backend for Windows ML. We now have full optimization across the stack, and as a result, the trained networks that we train in all these different types of networks and all these different types of frameworks can now have the opportunity to be deployed into the world's hyperscale data centers. Four brand new capabilities addressing literally the entire stack of the workloads. Still lots and lots of work that we have to do in collaborating with all of you in your hyperscale data centers. But if we're successful in doing so, the millions of hyperscale servers can now be accelerated. Up until now, we've only been able to accelerate just those ones that are really focused on image and video. But in the future, starting with this generation, starting with today, we can now accelerate voice, speech, natural language understanding, recommender systems, as well as images and videos. Well, we've pulled together some of the latest results. It's really, truly amazing. Images are accelerated 190 times. Natural language, this is the Google Natural Machine Translator, GNMT for natural language understanding, 50 times. The neural collaborative filter that is in the SAP recommendation system that IBM recently announced as well, those architectures, NCF has been accelerated 45 times. Speech synthesis, WaveNet, 36 times, and speech recognition, 60 times. If we just assume that video and images and speech and voice and all of that stuff is all on balance approximately equal load, in aggregate, we're going to speed up hyperscale data centers with our GPUs with this generation of optimizations 100x. We would increase the throughput by 100x. Or another way of saying it is we're going to save a lot of money. You guys, come on, we've done this before. You guys know the drill. The more you buy, the more you save. And with 100x speed up, just imagine how much you will save. Well, now that we have all these accelerated frameworks and all these accelerated code, how do we deploy it into the world's data centers? Well, it turns out there's this thing called Kubernetes. Ladies and gentlemen, today, yeah, it's okay. I know. Kubernetes on NVIDIA GPUs. Kubernetes on NVIDIA GPUs. Kubernetes on NVIDIA GPUs is going to bring so much joy. So much joy. There are people watching this out on the web going, that guy's lost it. That brings joy? Wow. Yes, this is going to bring joy. And this is going to bring joy because Kubernetes allows us to take these massive workloads that are servicing billions of people, and it's an orchestration layer that orchestrates the workload that's coming in from the cloud and orchestrated across the resources of the hyperscale data center. Lots of CPUs and lots of memories, lots of networking, lots of storage, and it needs to orchestrate it across the sea of servers. And today, it is GPU aware, and it's GPU accelerated. So Kubernetes is now GPU aware. The Docker container is now GPU accelerated. You've got all of the frameworks that I talked about, which is GPU accelerated. And now you got all these inferencing workloads that are now GPU accelerated. And you've got NVIDIA GPUs in all these clouds, and NVIDIA GPUs in all these data centers and servers. And you've got this incredible, wonderful orchestration layer system software called Kubernetes. Life is complete. Okay, let me show it to you. Guys, Justin. This is Justin. Justin is, of course, you guys have seen this flowers before. Now, we're going to do the flowers a little bit differently today. So this is flowers, of course, running on CPUs, four images per second, and the fastest Skylake that we have. And so, Justin, take it away, sir.
Yeah, absolutely.
Oh, Ryan, excuse me. I'm sorry. Is Ryan?
Yeah,
Justin's
I was wondering
coming
if
up.
we're going to switch it up, but Justin got nervous.
I'm sorry. No, it's not me.
Absolutely. So, as you said, like TensorRT and inference performance, we've laid out the value for it right here. So this is the miracle of deep learning, showing flowers using ResNet 152 on Intel's latest Skylake CPU. So if we click on these, we can see these flowers.
Pelargonium. That's a Snapdragon. Hey, guys. Wow. Come on. That's industry stuff. People in the tech industry, we should go, you recognize, I didn't know that it was a flower. It's awesome. Fritilia, okay? Blanket flower. Okay, so now show us what it looks like on a GPU. So Ryan, this is now running on NVIDIA GPUs, okay? So this is Volta, right?
Yep.
This is what? Hey, guys, yeah, that's right. The more you buy, the more you save. Okay, check this out. Ryan, so this is one GPU.
One GPU.
This is one GPU.
Exact same network.
This is one GPU?
Yep.
That's nuts. This is one GPU. How are we going to make it a living if this is one GPU? So this is one GPU. Okay? And so suppose, okay, well, let's Kubernetes this thing.
Yep, we got it running in Kubernetes. So imagine like our app gets so popular, everyone wants to know about flowers, and we get a larger load. So we're going to scale this up. Let's look at what a larger load looks like. So there we go. That's a larger load, so we need to handle that load. So what we do is we can ask Kubernetes to say, hey, let's make multiple replicas of that same container. And so I'm going to add 8 replicas in. You're going to see them come in. And I'm going to add them into the load balancer. And as I add them in, you're going to see it just get faster.
Wow.
That.
Guys, this is like magic. Kubernetes is orchestrating this data center. And what's amazing is this. So Kubernetes assigns this pod, which is basically a service or an application that contains a whole lot of containers. Okay? It could assign this pod on one GPU, on many GPUs in one server, on many GPUs and many servers. It can also assign it across data centers. So you could have some of it in the cloud and some of it in a data center. You could have some of it in this cloud, some of it in that cloud. Truly amazing. And all of this stuff is happening completely invisibly because we've made Kubernetes GPU aware, and because the NVIDIA architecture and all those containers are literally everywhere. And so as a result, this magic could happen because the foundation we've been layering and we've been growing now for several years is now come together. And this moment, the Kubernetes moment, pulled it all together. Ryan, what else you got for us?
So as you said, not only can we run it in our local on-prem data center, but we can scale and we can burst into the cloud. So let's take a look at that right now. So I'm going to
Saturn V is at the NVIDIA, our NVIDIA data center. It's our supercomputer. There are 660 DGXs in Saturn V today. So 660 petaflops. It's about to get upgraded, as you can imagine.
It's going to get exciting. So I'm going to add 4 more from the cloud. So this is going to be an example of cloud bursting or cloud fallover. So here we've turned on 4 in the cloud. They're active. And what I'm going to do now is show you self-healing. So I'm going to kill off 4 of these GPUs that are running right now on Saturn V. And what you're going to see, and you're going to have to watch really closely, is we're going to take a bit of a performance hit. And then those AWS GPUs are going to jump right in, and the performance is going to come back up. Ready? There they go down. You didn't even see it this time. Sometimes it's that fast.
Wow, that's an incredibly good demo. Ladies and gentlemen, this is a demo of resilience. A demo of resilience where before and after is exactly the same. I bet you really enjoyed that. We don't have to show it again because guess what, guys? It looks exactly the same. Okay? A demonstration of resilience. And this is one of the most amazing things about modern hyperscale computing. And we now have cloud to cloud. We have any cloud. We have cloud to prem. We have any prem. And so the NVIDIA architecture, all of these frameworks, all GPU accelerated, is now possible, orchestrated under Kubernetes so that it can basically run everywhere. Ladies and gentlemen, Ryan. So, the NVIDIA Kubernetes on NVIDIA GPUs. Kubernetes on NVIDIA GPUs. Super exciting about that. The inference movement on our GPUs is really moving fast. We now have up to 40,000 downloads, I think, of TRT, and it's just picking up steam. And the reason for that is because all these different companies are developing their networks and models, and it's time to deploy them. And they want to deploy them into servers. They want to deploy them into PCs, WinML. You want to deploy them at the edge, IoT devices on NVIDIA Jetsons. You want to deploy them on supercomputers. You want to deploy them on hyperscale. You want to deploy them inside companies with SAP. The number of ways you could deploy software is, of course, quite large. And now, with all of our new battery of accelerations for inference and Kubernetes on NVIDIA GPUs, we can now literally blanket the world with this new approach. So super excited to do that. Ladies and gentlemen, the NVIDIA AI inference. So this is the NVIDIA AI platform. Today we announced that the GPU Volta has been doubled in memory size to 32 gig. It's now available in DGXs and available in the cloud soon. NGC is now on AWS, GCP, AliCloud, and Oracle, and more are being certified. We're certifying them as fast as we can. The NVIDIA GPU cloud now has 30 optimized GPU containers, and this year, we announced 4 new battery of acceleration capabilities for inference. New TensorRT 4.0 that is able to handle RNNs and sequence-to-sequence type of models, TensorFlow deep integration, Caldi acceleration, which is the most popular speech recognition system, Onyx, an industry standard backend for inference, and WinML optimization into that. And sorry to say, Titan V is still out of stock. Apparently, the popularity of Titan V is quite high. And so we'll make them as fast as we can, and we'll put them back in the store. And if you could just be patient. Lots of Titan Vs being sold. The NVIDIA AI platform. You know, all of this, one of the things that, as I was reflecting on this keynote, one of the things that just gives me so much pride, and it's such a great creation, is NVIDIA Research. For 10 years, Bill Dally has been building NVIDIA Research. Bill Dally is my chief scientist, and he's the head of NVIDIA Research, and it's 200 people strong, but the productivity of this organization is just utterly incredible. They're doing fundamental and basic research across the entire stack of computing. You know, the number of fundamental basic research, computer science, industrial computer science organizations, research organizations that are working across the entire stack, all the way from circuits to networks, to parallel processor architectures, programming models, all the way to computer graphics and deep learning. Those aren't that many. And this is 200 people strong across the world. And the thing that's really special about the way we do NVIDIA Research, it's really a hub and spoke system. They're collaborating and doing research with all of the product research teams. We have hundreds of researchers around the company, all working together to advance the future of computing. Some of their contributions you have already seen. NVIDIA Research initially started RTX, and the 10 years worth of work that they've done has resulted in the NVIDIA RTX, or NVIDIA Optics and NVIDIA RTX technology. NVIDIA Switch that was described today that made the world's largest GPU. cuDNN, the library that has now revolutionized deep learning, all originated at NVIDIA Research. I'm so proud of these guys. And you guys have seen some of the really amazing work. Progressive GAN that was recently described that caught a lot of attention because of the amazingly realistic faces that it's able to generate. And this is one of my favorite technologies. Noise-to-noise denoising. Noise-to-noise denoising. That's one too many times you said noise. But that's got to be incredibly good technology. I showed it to you earlier today. It's basically super rays. So wherever these black dots are, ray tracing hasn't completed yet, but somehow using artificial intelligence, we're able to predict what color and what light it should have been and put that up on the screen in advance, finishing the frame much, much faster. Okay, so let me show you one thing here. This is, what you're about to see here is this. Imagine we taught a network how to draw. But we wanted to teach this network how to draw photorealistic images. And so what you're looking at here is, of course, a road. You can imagine that as a road, just like that. Based on our intelligence and based on all of our experience, we know that that's a road. The pink, what is that color? Is that purple? Fuchsia? That's fuchsia? Okay, fuchsia is roads. Blue is cars. Posts are yellow. Green is obviously trees, and gray, that's got to be buildings. And we take this image, and we put it into the artificial intelligence network, and we say to it, produce a photorealistic image. And this is what it did. Okay, we trained this network to do this, and now it's going to create photorealistic images. All from this. What do you guys think? Is that just amazing? So this artificial intelligence network is actually synthesizing information, and we're teaching it to synthesize roads, things that you would see on roads, and synthesize it in a photorealistic way. Ladies and gentlemen, NVIDIA Research is now all over the world. I'm so proud of this team. Here's Seattle, Redmond, Santa Clara, of course, Salt Lake City, Austin, St. Louis, Westford, Virginia, Charlottesville, Durham, North Carolina, Helsinki, Lund, Berlin. Some of the greatest cities around the world, 200 people strong. We're growing. Reach out to us. We love to work with you.